So one observation, though we don't have a proof for this, but we have observed from all these classes that if the number of cubic terms is less, first priority is on cubic term. So if the number of cubic term is less, so the area, the S-box class becomes more area and power efficient. And suppose if the number of cubic terms are same, then the sum of linear terms and the quadratic terms has to be less to make it more area efficient, area and power efficient. So then we went further and we optimized the function, that local rule having algebraic degree 3, to make it, we decomposed that function into two functions with algebraic degree 2, and we obtained a more optimized area efficient TI, that is we call it as a composite TI, where in the first clock cycle we obtained the intermediate values, in the next clock cycle we obtained the final values for the S boxes. So using that, if you see, we have still reduced the area further, and for class 131 we noticed like we have almost reduced 80% from our previous implementation, from algebraic degree 3 to algebraic degree 2, decomposing that function. And then followed, we have evaluated our design using fixed versus random text vector leakage assessment, and we have collected 1 million trace for that, and we obtained a value of minus 0.42 plus 0.3, and the permissible range is minus 4.5 to plus 4.5. So we can conclude that our design is also side channel secure design. So now we have designed two applications based on this S-box. First one is completely focusing on the area. Now what we observe is if the diffusion layer is less, then we need more rounds, and that will degrade our throughput. So for present we have a branch number 3, and for GIFT we have branch number 2. But GIFT S-box possesses a BOGI property, which they utilize and reduce the number of rounds to 28. But if we use our S-box with the bit permutation, we get more number of rounds because we do not have the BOGI property. But this paradigm has the least area because permutation doesn't consume area. So for using this paradigm, we are able to show that our design is optimized in terms of area. Next is design paradigm 2, where we are using almost MDS. Almost MDS has better diffusion, so we get a better higher throughput. So since the number of rounds are less in that, so with that we could reduce the number of rounds from 40 to 16. But the problem with this design paradigm is the area would be a bit more because of the MDS layer, almost MDS layer. So this is the table where we compared the other block ciphers along with our CA based one. So we have with this class we have seen that with 16 S boxes and diffusion layer we obtained an area of 2253 with 131 class of CA based S box with this is the G in 180 nanometer, and this is the throughput that we have obtained with almost MDS. So with almost MDS, throughput increases, but area throughput is good, but the area degrades. But with bit permutation, area reduces, but throughput becomes much better. We have also explored the non-optimal S boxes. Like for example, there are other S boxes, the other rules which does not follow the which does not follow the optimal property. We have explored all those non-optimal CA-based S boxes also, but we found that those S boxes are not suitable. I mean, those CA rules are not suitable to construct a CA-based S box, as they do not have BOGI property, and even the nonlinearity is also not good. So in a future work, we will extend this to 8x8 CA-based test boxes, and we are considering this as a design for the NIST submission, which for this design as a theme for the NIST submission. Thank you.
Thank you very much. Questions? Yes.
Thank you. Thank you for the talk. Can you go to slide number 18, please, where you showed the construction that you have? Yeah, I have actually 2 or 3 questions. One is, what is the latency of your design here? Means that for just given one input to this box, you need a couple of clock cycles, if I have understood correctly.
Yeah.
How many clock cycles you need?
4 clock cycles.
4 clock cycles.
Yeah.
And then you are switching the shared input to be given to the same circuit.
Yes.
And then this changing between the shared input is already known that is leaky. You cannot easily just change the input of this box, which is shared, to the one circuit. You should have some pre-charging state in between. Otherwise, the shares that you have, they will be overwritten on each other, at least on the signals, and then you may already violate the non-completeness property.
But if we implement this in different modules, then it won't violate the leak. I mean, it won't leaking. In that case, I mean, if we implement in them with the keep hierarchy on option in different modules, then it won't be.
Then why do you need 4 clock cycles if there are 4 different modules?
Yeah, but 4 clock cycles is required because in each clock cycle, we are obtaining 1 bit of output of the S box.
But then you use the same circuit, the same sub-circuit, to make the other, let's say, bit of the SPOX output, or share of the SPOX output.
Share of the S box output.
Yeah, then as I said, you have shared input to the circuit, and you just change the input to the SPOX, which is shared again. You mean you swap some shares to the SPOX. Probably we need to discuss about this in offline, yeah? Okay. Because it probably takes longer. My second question is, how do you achieve here or guarantee uniformity?
Yeah, so uniformity is we have the expressions, like when we decompose a Boolean expression into the number of shares, we check the uniformity using the uniformity table. Like if the values comes 0 or a specific single value, then it's uniform. So whatever for this class 131 and 122, whatever, so we have, I think we have the expressions, I think, wait. Oh, I think that slide I don't have, but we have it in our paper that when we decompose this expression, like class 122 or 133 using 3 share, we have all those expressions checked with our, it is meeting the uniformity.
But you consider the uniformity only for one single bit of the SPOX output, or just for all of the outputs? Because you cannot just consider one part of the SPOX output and say this is uniform, and then if I can concatenate the other uniform output, the result will be uniform.
No, we are considering all the outputs okay, uniform, because if we divide this expression into 3 output shares, then those 3 functions are all uniform. It will follow the uniformity property. Okay. Now, since we are using the same function, so it will follow the uniformity property overall.
Okay. Thank you.
And yeah.
Thank you for the talk. You compared your S boxes with other S boxes, but the cost mostly depends on the implementation, not that much on the S box. So what implementations did you use for these existing S boxes?
We used what implementation? The function LUT based optimization for other S boxes and for our function based.
Okay.
Any other question to Rajat? Okay, if not, let's thank Rajat again. Thank you. And so the last talk in the session is a presentation of a platform for evaluation, implementation, and generation of S boxes. The paper is by Zhenzhen Bao, Jianguo, Sang Li, and Yu Sasaki, and Zhenzhen Bao will give the talk.
Thanks for the introduction. So I would like to introduce our SOK paper on the design of SBox and a platform for evaluation, implementation, and generation of SBox. So many block cipher follow the Shannon idea, sequentially application of the confusion and diffusion. Confusion are generally provided by the form of substitution box, so SBox for short. The natural question is how to distinguish the good SBox from the bad SBox. So, developed for the several decades, the design criteria on SBox have been involved, and both for the security respect and the implementation performance aspect. So, in this talk, in this paper, we aim to provide a survey on the known results on the design criteria of SBox, and also build a platform for assist the evaluation, implementation, and generation of SBox. And I will introduce the three aspects of functionality of SBox, and would like to use the green ball to indicate that Pagan can provide the functionality efficiently, and use the yellow ball to indicate that Pagan is only efficient for small SBox, and use the red ball to indicate the corresponding functionality is currently not supported by Pagan currently. So SBox, an SBox mapping NB to M bits will have M coordinates, and they are the n-variable Boolean function. We denote them use SEI. And there are many ways to represent an SBox. The direct way is use the lookup table. And also there is a bit-slice representation. And they are the concatenate of the value vector of the coordinates. So both of the representation can be accepted as input to Pagan. Besides, there is also mathematical representation. A general conventional way is use the algebraic normal form. So use this formula. Given the value vector of the Boolean function, we can compute efficiently the algebraic normal form. So given the bit-slice representation of an SBox, Pagan will output the algebraic normal form of the coordinates. So we want to make a distinguish between the coordinates and the components of the SBox, because some property can only be defined use the components. The components are the linear combination of the coordinates. We say an SBox is balanced if they take every value the same number of times. So if all of the components are balanced, the Boolean function, the S-box is balanced. The balanced S-box mapping n bit to n bit are of particular interest. They are the permutation. So let's look into the security aspect. With respect to the resistance to differential cryptanalysis, the property of the derivative of the S-box can provide some quantify the strength of the S-box. So the solution of the derivative equation can be formed into this well-known difference distribution table, and Pagan will compute the maximum in this table, and this is well known as the differential uniformity. Our community are still seeking for larger S-box with even dimensional because they are good for the resistance to differential analysis. So besides the maximum, the frequency of the maximum occurs in this DDT, and also the frequency of the values in this table may also provide distinguish between S-box with the same uniformity, because they can behave differently for specific cipher and provide more accurate upper bound for example, 2 round of the upper bound on the maximum expected differential probability of the cipher, for example, for AES. So Pagan will compute the frequency, the differential spectrum, and for the resistance to linear cryptanalysis, the property of the Walsh transform and the Walsh coefficients are important criteria, and they are related. The Walsh coefficient is related with the pairs of the linear approximation. So we call this the table formed by the coefficient Walsh coefficient. Say as the linear approximation table, and again the maximum in this the maximum in this table, the absolute value is defined as the linearity, and we also desire S-box with small linearity, and again, the frequency of the maximum occurs in this table, and the whole Walsh spectrum can also provide distinguish between S-box with the same linearity. So given an S-box, Pagan will evaluate the spectrum, the Walsh spectrum. For some cipher, their linear layer only consists of bit permutation. So the S-box not only provide some confusion, but also some diffusion. So the differential branch number and the linear branch number may be the criteria for the design. So now we focus on the subtable in the DDT and the LAT. They are named the DDT1 and LAT1. And so the maximum in those subtables, and also the number of non-zero entries in these subtables are of significance for some cipher. So Pagan will output the difference distribution in this form. It will rearrange the rows and the columns so that they are in the Hamming-Weight order, so that we can clearly see the DDT in the left upper corner, and also output the uniformity and the spectrum when see the subtables. So for an S-box can be completely specified by the linear approximation table. So it's possible to recover the S-box from the LAT, and also from some good DDT, we may recover some DDT equivalence class of S-box. However, this functionality is currently not supported by Pagan. So as mentioned by yesterday's talk, the resistance to boomerang attack may related with the boomerang connectivity table. And again, there is a boomerang uniformity, the boomerang differential spectrum that may interest for evaluate. So Pagan will compute this BCT. And for the resistance to algebraic attack, the maximum among the degrees of all components and the minimum among the degree of the components may be important. So besides the frequency of the degree may important, so Pagan will compute the maximum degree, the minimum degree, and the degree spectrum according to the ANF of the components of the S-box. So besides the degree of the linear combination of the coordinates, the product of the degree, the maximum degree of the product of K coordinates can also useful because they may be used to in the division property based attack. And for given an S-box, Pagan will evaluate this DK and output a table like this. Besides, this DK can also provide some accurate, more accurate estimation for the degree of the whole cipher. According to this theorem. So besides DK, which is related with the division property-based integral attack, there is another notion, the site, which shows the appearance of monomials in the ANF of the product of the coordinates of S-box can be important because they may show some resistance of the S-box against the division property-based attack. So Pagan will evaluate the table representation of this table. And for besides the algebraic normal form, which is a multivariant polynomial representation, the S-box can also be uniquely represented by the univariant polynomial. The univariant degree and the number of terms in the univariant polynomial representation may be important, but currently Pagan do not evaluate. And for the resistance to truncated differential and the subspace trio attack, the linear structure of the S-box may be important because when evaluate the longest subspace trio, if the S-box have linear structure, we should consider this. Besides, the linear structure of the Boolean function is actually a very early notion to provide a measurement on the linearity of the Boolean function. And the linear structure of the S-box has been used in very early differential-like attacks on DES. So given an S-box, Pagan will output the linear structure of the S-box. So there use an efficient way to find all linear structures. Use the autocorrelation table formed by the autocorrelation coefficient of the components of the S-box. So given an S-box, Pagan will output the autocorrelation table also. For the resistance to some cube-like attack, the notion of VW linearity may be important because it can quantify the ability of the S-box to propagate fine relations. So an S-box is VW linear if there exists two linear subspace, the input subspace V and the output subspace W of dimension small v and W, such that all components of the S-box in this output subspace W are affine on all coset of the input subspace. So given an S-box, Pagan will evaluate the VW linearity of the S-box and output a table like this. It shows the number of subspace V of dimension V such that there exists a W-dimensional W such that the S-box is VW linear, and also output all the subspace VW. And as mentioned by the first day's talk, the resistance to invariant subspace attack may related to the existence of the nonlinear invariant of the S-box, especially the quadratic ones. So maybe it's of interest to evaluate the nonlinear invariant of the S-box. But currently, Pagan do not suppose this functionality. So lots of the previous mentioned cryptographic property are invariant under some transformation. For example, the linear transformation, the permutation transformation. And the knowledge on the largest transformation group that preserve criteria is very important to study such criteria, and also to reduce the space of the S-box we should focus on. So given S-box, Pagan will evaluate the representative of its permutation XOR equivalence class, and also the representative of its linear equivalence class, and test whether two S-box are Fan equivalent. And if they are equivalent, it will output the Fan permutations. However, the two more general concept of equivalence are the extended Fan equivalence and the CCZ equivalence. However, Pagan currently do not evaluate this equivalence. So this previous is on the security aspect. On the implementation aspect, we first provide a survey on existing tools. And through the comparison, we found a tool named Lighter provided by Jen, etc., have the most features, and the speed is acceptable, and they are open code. So we want to build the implementation aspect of functionality based on Lighter. So given S-box, Pagan will evaluate the implementations good in terms of the following performance criteria: the bit slice gate complexity, the gate equivalence complexity, the multiplicative complexity, and the depth complexity. And inherent from Lighter, Pagan can consider that different gates can have different cost, both for the gate equivalence and the gate equivalence complexity and the depth complexity. So the approach in Lighter used the bidirectional Dijkstra's shortest path finding algorithm, and they expand two graphs, one from the identity function, and the other is the target function, the S-box, and use a meeting the middle strategy to find the implementation of the target. And the nodes are all developed, expanded, use the right-hand side kind of function. They are invertible. And so based on this approach, Pagan we propose some optimization method, because we found these two graphs are actually also isomorphic. And so actually we only need to compute one algorithm, one graph, and which is independent with the target. So by use the composition and concatenation method, we can find the implementation of the target. And because this graph can be pre-compute, and stored, so they can be used once for all. So we also use some equivalence between the implementation sequence to reduce the search space, so that Pagan is efficient even for given a large set of small SBox. And we want to enrich the functionality by make it cover some larger SBox and support finding the depth optimal implementation, while it's currently only efficient for 3 and 4-bit SBox. And for the generation aspect, we use the simple circuit construction method, which is very similar for the construction method of Lufa, the SBox of Lufa. Actually, it is a direct extension of the implementation functionality. It's still use the pre-compute graph and compose the nodes in the graph to get the composition function. And given a set of criteria, it checks the result whether fulfill such a set of criteria, and also use the invertible small functions. So the two usage of in Pagan is that if given a set of criteria together with the set of SBox, it can filter out those SBox fulfilling this criteria and output more detailed evaluations. And if only given a set of criteria, Pagan can generate some SBox, some new SBox fulfilling the given criteria, and classify the result according to their detailed properties. So let's make a summary. In this work, we try to provide a CV on the known result on the design of SBox, and we want to build a platform to assist the evaluation, implementation, and generation of SBox. However, Pagan is still missing some functionality, and it's not yet powerful enough for the implementation and generation of strong, larger SBox. So, but we believe there exists a heuristic and a theoretical method that can tackle the larger SBox and integrate into this platform. So, for interested readers, we refer to the GitHub website for the source code and all the generate results. Thanks for your attention.
Questions? Yeah.
Thank you for the talk. Suppose someone wanted to contribute code to this Pagan platform. What would be the best way to go about it? Through GitHub or?
Yeah, maybe GitHub.
Okay, thank you.
Other questions? Yes, Friedrich.
Did you do some benchmarking about the speed of your implementation compared to other open available implementations?
We just implement other tools and try some experiments, and it shows that there are the site-based method, and the site-based method is not very efficient for the implementation. And also there is the depth first search algorithm, and the output is not guaranteed to be optimal, but it is compatible with the letter-based method.
And for the security evaluation methods, did you also do some benchmarking?
Security, no.
So for this computing the differential uniformity and equivalence classes and stuff like this?
You mean the evaluation speed of the tool or the result?
No, say that if I have, I don't know, a large set of SBoxes and I want to pick the best from this set regarding some security notion, maybe for differential uniformity, So did you, and there are, I don't know, for example, SageMath can also do this. And did you compare your implementation speed-wise to the implementation from Sage?
I tried Sage first, but for large set of Xbox, Sage does not provide the result efficiently.
Okay, thanks.
And for this tour, we can evaluate to the, for example, 20 or Xbox simultaneously efficiently.
Okay.
Any other question?
Well, I have one. So, how hard would it be to add, for example, another design criteria in your tool? Like, is it based on a lot of small modules, and you can add the small module which says, well, I have another criteria for my boxes, and I plug the module, and everything will work correctly? Or do you need to do a bit more technical works in the code to make it work? I don't know.
You need to evaluate the given Xbox.
Yeah.
You can write the lookup table representation in the file. The pagan will read the file to generate the evaluation.
No, this was more in the other way. Like, imagine that I found some new design criteria for Xboxes.
Yeah, you can.
Is it
you
easy
have
to add it?
Code a file named func. This file provides the class, the CPP class, and you can add new functions to this class,
Okay.
and to evaluate new criteria.
Okay, thank you.
Is there any other question? So I think you will get some new contribution to this tool. So thanks very much. Let's thank all speakers of the session. We now have lunch, and the next session starts at 2 o'clock.
Okay. In
in 4 weeks, so next month. Whoa. Yeah, it took some time because, I mean, we have some problem with the bureaucracy. With bureaucracy in TU. So the documents and...
Okay. So what's your next move?
Well, I promised Christian that I stayed in Graz until December at least.
Okay.
And then I have to decide, yeah.
Okay.
But you say that the postdoc should start as soon as possible, you said.
Yeah, so you will be there and here is field, so it's really up to you. Yeah, but I'm quite optimistic about the funding, so it's okay? Yeah, it's okay. So I guess we will be there. You will be there.
Because also my proposed me a postdoc here at TheIACR for 2 years.
Okay.
So
wow, I got a very tough.
Lunch is on the first floor.
Okay.
Yeah, but for example, what about my girlfriend? I mean, because we are not married.
Yeah.
So I guess I can get the visa, but what about she? And
So you will need some. I know in France you got some unofficial marriage certificate, something like that. So you will need something like that to sponsor a visa
Hello, good afternoon. So here we are going to have the third talk of this FSC. This year, now we have Gojian. And Gojian is an assistant professor in NTU in Singapore. He's well known for being a co-designer of the LED block cipher, photon hash function, and a few algorithms that have been submitted to the CSR competition, so Marble, Silk, and Clock. And since a few years, Gian started to analyze SHA-3 based structure. And I think today we'll talk a bit more about this for 1 hour. Thank you.
Thanks for the introduction, Jeremy. So the title of the talk is Security of SHA-3 and Related Constructions. So I was so lucky to have so many collaborators on this topic. I should say that I'm only summarizing the results on their behalf because they did most of the work. So the talk is divided to 6 sections. So first of all, I will introduce Keccak. So the research community is more used to use the word Keccak rather than SHA-3 now, still. And then I will go for 4 different aspects of the security: preimage, collision, distinguisher, and key recovery. Finally, I will give the concluding remark. So the SHA-3 hash function is following the sponge construction, which means that you start with initial value and apply this permutation iteratively. To process the message, you break the message into blocks and fit into the first few bits of the states. And XOR it, apply the permutation. XOR it, apply the permutation. Until you process all the messages. After that, you come to the squeezing phase, where you output several bits of the first few bits of the internal states. You repeat this process if the number of digits is not sufficient, until you get enough output bits. So for Keccak, we have a permutation of B bits, and there are several parameters, R and C. R is what we call bit rates, and C is the capacity. So R plus C is a B. So each core of the permutation processes R bits of the message. So when you have the sponge, what's left for us to define hash function is to define the permutation F and the parameter RC as well. So for SHA-3, the Keccak F is the underlying permutation. It is 1,600 bits internal states, can be seen as 5 by 5 array, and each of them is of 64 bits, and it has 24 rounds. Each of them consists of 5 operations: zeta, rho, pi, chi, and iota. And we'll introduce each of the 5 operations. Note that chi here is the only nonlinear operation. All the rest are linear. So zeta is a diffusion layer, adding 2 columns into the current states, meaning that to update these states, what we do is to calculate the sum of the 2 neighboring columns. So this column is actually one slice before this current state, and this column is actually next to the bits. So you sum these 2 columns together, add this sum into the current state. So that's what we call zeta. And there's a definition of a kernel parity, column parity kernel, meaning that if all the sum of the columns are 0, then the state is in CB kernel. Of course, if all the sums are 1, it's also in CB kernel, because then if you add these 2, 1 together, you will get 0. So this is very important for us to find differential parsers. Rho is a rotation within the lane. So there's a different rotation constant defined for each row. Yeah. And pi is intra-lane permutation, meaning you change the position of the lanes. For example, you get 1, 0 here, and here after the pi, 1, 0 becomes here. So the value doesn't change except the position. And the only nonlinear operation is the chi. We usually call it the S-box. And what it does is to XOR. So what it does is to produce 5 bits from the 5 bits inputs, and what it, on individually Y0, the first bit is actually the sum of X0 plus the inversion of X1 times X2. So that's the only nonlinear portion, this multiplication. So clearly you can see that the algebraic degree of S-box is 2 and the inversion is 3. So iota as a round dependent constant to the states. The round function will be symmetric, all round will be the same, and fixed point exists is vulnerable to rotation attack, slide attack, etc. But rather than that, iota doesn't play a role in most of the curve analysis. So in what follows, we will mostly ignore iota. So this is the round function. We have theta, rho, pi, chi, and iota. And we define the linear layer to be the composition of theta, rho, pi, because these 3 steps are all linear, and chi is the only linear step. And we ignore iota. Yeah? For preimage, the core idea is that when we treat the bits of message block as variables, we can convert the problem of preimage finding into a system of equations, and the algebraic degree of variables is kept to be at most 1 for as many rounds as possible. And this can be achieved by limiting the algebraic degrees increased by chi. As we can see just now, the chi actually take the product of 2 neighboring variables, and it actually increased the algebraic degree, but there's some way for us to limit this increment. The second method is to limit the diffusion efforts of theta by forcing the variables in CB kernel. Yeah, we'll see. So to keep chi linear, if we look at the expression of chi, the algebraic degree is 2, and the observation is that when there's no neighboring variables in the inputs of an S-box, the application of chi does not increase the algebraic degree, meaning that when we choose the variables, we choose variables not neighboring to each other among all the 5 bits of the S-box. So for example, if we choose the first and third bits of the S-box to be variables and the rest to be constants like 0, 1s, if you calculate the expression of the output bits, it will be variables, constants, and might be a variable or constant here, depending on the inputs constants. So, yeah, so as we can see, these 2 variables are not neighboring to each other, so this multiplication will not happen among the variables. So after the application of the chi, all the output bits are still kept to be linear, so with algebraic degree at most 1. But if you have 2 neighboring variables, then the multiplication of these 2 will increase the algebraic degree from 1 to 2. So this is something what we want to avoid. So if we can avoid this for many rounds, then we can keep the algebraic degree to be 1 for many rounds as well. So this is what we do within one S-box, and as we can see, it allows at most 2 independent variables, which also means that at least 3 bits out of 5 needs to be fixed in each S-box. So as we can see, we fixed the second, fourth, and fifth bits here. So we only have 2 variables. So of course, 1 bit variable is also fine. So this is a simple example of the linear structure. First of all, we start with linear inputs. After the application of round function, all the output bits are still linear, means algebraic degree 1. So here, the orange parts are the variables. The white parts are constants with value 0. The gray parts means constants 1, and the light gray parts constant 0. Sorry. The white parts are the constants, either 0 or 1. Okay. So to achieve this, as we can see already, at this point, we don't have any neighboring variables in every row. Yeah. So here, this one and this one, they are not neighboring to each other. Means that after chi, all the output bits will be still linear. But to achieve this, we still need to deal with the zeta. So zeta actually add the column sums into the individual bits. So to limit the propagation of the variables in this column, we actually force the column sum to be 0. Means that, for example, we can choose arbitrary variables for the first 4 bits and choose the 5th bit to be sum of the preceding 4. In that way, we can force the sum to be 0. And this is an example of a linear structure with 1 round, but of dimension up to 512. So our task is to find such linear structures for as many rounds as possible and with dimension size as large as possible. Because if we can cover more rounds, we can attack more rounds. And so if the dimension size is big enough, we can attack. We can make use of the variables for other purposes, like preimage finding. So let's see. So here's an example of a 2-round Keccak 512 preimage attack. So we choose, since we have one message block, the last 3 rows plus this lane is fixed to be a constant because it's defined by the IV. Okay, and what we can do is to choose the variables here, and again to limit the zeta effect, we force the sum of these two to be a constant, and here as well. And after the propagation of 1 round, everything is linear up to this point actually. So after the chi, it is linear, then it's followed by the linear operations. So everything here is linear. So preimage attack, in preimage attack, we are given the target. For Keccak 512, we actually have 8 lanes. So it's laid out in this way. So first row followed by 3 lanes here. We don't actually need to express the variables after the chi here. Instead, we can actually invert the chi using the values given targets here. Yeah. So in that way, we are actually using 1 round linear structure to attack 2 rounds Keccak 512. And since you have 4 lanes here and you have a condition of 0 here, 0 here, so you actually have variables up to 112 bits only. Yeah. For inversion, there are actually 3 different ways. If we look at the expression of the S-box, each output bit can be expressed by AI plus the inversion of AI plus 1 times AI plus 2. Yeah? So the first method is linearization. By linearization, we mean we force one of the 2 variables in the product to be a constant. Yeah? If one of them is constant, then everything will be linear. Yeah? But in this way, the dimension reduced by 1. Yeah? If you, for example, if you fix AI plus 2 to be 1, then you lose this variable. Yeah? So the dimension reduced by 1, and time complexity may increase depending on whether this reduction of dimension affect the final attack or not. However, the space preserves means that if you want to fix this to be a constant, you can brute force all the possible choices, means you try both 0 and 1, but you don't try them simultaneously, you try them one by one. So the overall space preserves. For exploration, what we do is we try to assume this one to be 0 because it's a product of 2 variables. So with chance 0.75 is 0. By this method, the time complexity increases. You have a probability here. Yeah, it doesn't always hold to be 0. and the space reduced by reduced to 3/4 because you only use the combinations where it leads to 0, like when this is 0 and when this is 1. Yeah. The last way to invert this is by what we call bilinear structure. So if you look at the 2 consecutive output bits, we can actually relate 2 consecutive output bits with 2 input bits by this expression. Yeah. So BI and BI plus 1 are the given targets, and AI and AI plus 2 are the input bits. So if this bit is known, yeah, either 1 or 0, this expression is linear. So given BI and BI plus 1, this equation becomes a linear equation. Yeah? So this actually preserves time and space simultaneously, but the limitation is that the knowledge of BI and BI plus 1 are not always there. It depends on the targets and the shape it forms. Yeah? So back to the example of 2-round Kerchak 512. So we already have the entire row here. So the knowledge of the entire row enables us to invert the chi for this S-box. So we are able to find all the corresponding values for this row. So already you can find the linear system with 64 times 5 bits. So that's already sufficient because you only have this many variables. And this gives you 320 bits equations. That's much more than what you got here. So by a simple inversion, this is already done. So in the first example, I showed the linear structure with everything to be linear, meaning that every bit in the states are linear. However, this is not necessary if those bits involved are not used to calculate the output targets. So for example, we know in Kerchak 384, the last 3 rows are not used because only the first 6 lanes are used at the output. So these are not used. So you don't really care about whether the last 3 rows of these states are linear or not. And similarly, if you want to just establish some linear equations out of this, you don't actually require all the bits inside the S-box to be linear. Some of them can be nonlinear, and as long as you have some bits to be linear, for you to establish the linear equation. So for example, I can assume the output bits of this one to be same as this one using our approximation. We have an approximation method assuming this output bits to be the same as the input bits. So with this to be linear, I can assume this to be linear as well, which equals to this one. So you don't really need the knowledge of all the rest bits to establish this. So keeping that in mind, we are actually looking for something which we call partial linearization. So we keep the linearization done for the first round, and we allow some algebraic degree 2 variables in the second round, and they will be propagated to more variables in the third round. But as long as these algebraic 2 variables are limited to specific positions, we are fine. This example, we are actually using one fully linearized round, one partial linearized round, plus one inversion round. Yeah. So this is how we cover 3 rounds for Kerchak 384. So in summary, using all the techniques combined, we can actually attack up to 4 rounds, SHA-3, 384, and 512. The complexities are actually slightly lower than the brute force. And we can see when we have more degree of freedom, means the R when we have more output bits, we can actually establish more equations. That's why when we have the bigger numbers here, we can actually attack more rounds. And the practical attacks are actually limited to very few rounds. For example, the most number of practical attack is shake 128 for 3 rounds only, and for SHA-3 variants is only for 2 rounds and 1 round. Yeah. And this is the status of the Ketchup Crunchy crypto preimage context as of today. Yeah. So the difference is that the rate here is much bigger than the SHA-3 variant. So for this one is 1440. The capacity is set to be 160 bits. And for this case, we can actually practically find the preimage for 4 rounds. And for 3 rounds variants, there are more variants attacked because with smaller states, if you compare this one with this one, the rate size is actually much smaller, means that the attacker has much less degree of freedom. So it becomes much more difficult to attack small variants. So you can see 3 rounds variants for this 800 bits internal states and 400 bits internal states are attacked, but this is not the case for the 4 rounds variants. So that's for the preimage. For collision, this is the status. The most number of attacked round is 6. This is applied to the Ketchup challenge. And for SHA-3 variants, the most number attacked rounds is 5. And this applies to the variants with bigger R only. So 256, 224, and 128. For larger output sizes, we actually attack lesser rounds, like 4 for SHA-3, 384, and 3 for SHA-3, 512. Yeah? So generally, the attack becomes more difficult for smaller R and larger C. So let's look at how we do it. This work is, this is the general framework of the attack. So we have a differential chair, and for this differential chair, we have a fixed input difference and a fixed output difference. And we have what we call connector here, which connects the initial value to the input difference of the differential. And depending on what technique we use, this number of rounds covered by the connector actually varies. So Itai et al. In 2013 actually find this for 1 round connector. And we later extended this to 2 and 3. Yeah? The requirements of the differential chair is that the first few bits of the output should have difference 0 because they are the outputs. If the difference is 0 there, it means collision. Otherwise, it's not. Okay. There are several properties we use for this connector. The first one is what given the compatible I input-output differences, the solution sets actually form a affine subspace of size 2 or 4 or 8. So meaning if the DDT of this input-output differences is non-zero, then the solution set is automatically an affine subspace. And the second property is that given the output difference delta out, the compatible input differences actually contain at least 5 two-dimensional affine subspace. Okay, so by compatible we mean the DDT value is greater than 0. So given the output difference find all the input differences, and there are at least 5 two-dimensional affine subspaces among this set. So the connector works, as I mentioned just now. Given the input differences, what we want to do is to connect the initial value to the input differences. So we have a linear layer followed by the chi. So what we do here is we know the output difference of the chi. So we want to bypass the chi by inverting the chi. Yeah. So the first step is to find a compatible beta 0, which is possible to be linked to this input difference through the chi. And yet we need to enforce that the portion of the capacity is 0, because that's what you cannot control. So they are forced to be equal, means that if you do the linear inverse of the beta 0 and get the alpha 0, the last C bits of alpha 0 needs to be 0. Yeah? So means no difference. And in the value phase, under the fixed beta 0 from above, we obtain a subspace of inputs X that leads to delta Si under P1. So let's look at P1. Yeah. So this is given, and once we fix the delta in, the solution set is actually forming a subspace. Yeah. So if we fix a compatible beta 0, for each S box, we are able to obtain the affine subspace. And for the entire state, we are getting a very big affine subspace. And we also need to ensure that the value of capacity part is also 0. See? So fulfilling these two conditions, then we are getting a one-round connector. And there's a way to extend this to 2 rounds by fully linearizing the chi layer. So from here to here, what we do is we actually prepend 1 round before this. So since in each round there's a chi layer, what we do is to fully linearize this chi layer so that the L, the chi layer plus the L, becomes a very big linear layer. Yeah. So by fully linearize, what we mean is if we restrict the input values into a subset, then the expression of the S box is actually equivalent to some linear transformation. So for example, if we limit the input space into this affine subspace by fixing x1, x3, x4 to be 0, the S box expression is actually equivalent with this matrix multiplication. So if we do this for all the S boxes in the chi layer in the first round, we can do full linearization. However, full linearization allows dimension at most 2 out of 5 affine subspaces. So it means that we have to fix at least 3 bits in each linearization of S boxes. So such linearization can be done at once, only once, at most once, because you lose 3 bits out of 5 doing this once. So if you want to do it twice, you will need 6 out of 5 bits. So that's already insufficient. But we have a method to solve this by what we call non-full S-box linearization. So we observe that if we have 2 round connector, the second chi layer, in the second chi layer, not all the S boxes are active, only few of them. So we don't really need to linearize all the input bits here. We only care about those active S boxes. For the S boxes which are not active, we don't really need the input bits to be linear. So what we do is we trace what bits are needed in this in the chi1 layer and propagate back this condition into this chi0 layer. And we only, so once we know what it is in the outputs of chi0, we know which are the S boxes to be linearized. Yeah? So we only linearize those active boxes of X chi1, which matters, so which may come from the active or inactive S boxes of chi0. So it means that even for the chi0 layer, not all the S boxes are active. So we'll see for partial linearization, what happens when the S boxes are active and non-active. So here's an example. If we only want two output bits of the S boxes to be linear, for example, B0, B1 here. So what we can do is actually simple. If we simply fix A2 to B0, the expression of B0 and B1 will be linear immediately. Yeah. So this costs only 1 bit linearization versus 3 bits for full linearization. So we actually save 2 bits degree of freedom here. So here's a summary of the linearization needed. So depending on the Hamming weights of the inputs, so if the Hamming weight of the input mask is 5, means all the bits need to be linearized. We already know 3 equations are needed, so we have to linearize 3 bits. For if only one, okay, this is 0, so means none of the bits are needed in the chi1 layer, so we don't need any linear equation. For other cases, we might need 1 or 2. But notice that for fully linearization, for all these cases, we need 3 bits. Yeah. And for active S boxes, there's a case when where we need only 2 equations instead of 3. Yeah. So we save quite a lot of degree of freedom by doing this, and then we can make use of this degree of freedom, meaning linear bits, to fulfill some S boxes in the third round. So by this, we actually have done a linearization for the first 2 rounds. So all the active S boxes are fulfilled automatically, plus some of the S boxes in the third round. And this is for the connector layer. For the differential layer, what we do is we try to find high probability differentials. And this is usually done by forcing the second and third round of the chair to be CB kernel. So once you force it to be CB kernel, the theta effect is limited, meaning once it's in CB kernel, the theta becomes the identity. So it doesn't propagate the differences into other places. And the second condition, as I mentioned, the first D bits of the output differences should be 0, so that this is a collision. And a general guideline is that this one should consume as less possible degree of freedom as possible, and provided by, because this consumption is actually provided by the connector. If we can consume less degree of freedom, you might be able to extend the connector for more rounds. And vice versa. If you require much more degree of freedom here, then the connector may be reduced to lesser rounds. Yeah. And to do that very efficiently, we actually did the brute force parts by GPU implementation. And it turns out to be very efficient for the NVIDIA GPU GTX 970. It actually capable to evaluate 2 to the 28 Keccak evaluations per second versus roughly 2 to the 21 on CPUs. So that's roughly 100 times faster than CPUs. And they are very cheap, actually. So one of these actually cost us around 500 Singapore dollars. That's roughly 300 euros 3 years ago. And this enables us a computation power up to 2 to the 50. Yeah? As the source code of the GPU implementation is available on our group websites. So this is the summary of the collision attack. Practical attacks are up to 5 rounds for some of the SHA-3 variants, and for the Keccak collision contest is up to 6 rounds. And as I mentioned, with a smaller internal state size, it's actually much more difficult to attack. So actually for the 200 bits variant, we can only attack only 1 round so far. And this is the status of the Keccak Crunchy Crypto collision context as of today. So 6 rounds can be attacked for the biggest internal state size. And for 5 rounds, there's 1 more variant to be attacked. Okay, that's for collision. And we come to distinguisher. How many minutes do I have? 25, okay. For distinguisher, we are actually utilizing the idea of linear structures. So we focus on zero-sum distinguisher. So that means given the function or permutation f, we find the input set x such that the sum of the inputs is 0, as well as the outputs of the sum of the outputs are 0 as well. And a natural way to find this is a linear space of dimension up to the degree of f plus 1 fulfills this, because if you have degree of f plus 1 dimension, then it's actually looking for the higher differential of this f function. So it will be 0. Yep. So what we do is we start with a linear structure of t rounds in the middle. We propagate this backwards for m rounds and forwards for n rounds. So for forwards and backwards rounds, depending on the round number, the algebraic degree is actually fixed. So for forward rounds, forward n rounds, the algebraic degree is 2 to the power of n. For backwards, since the chi-inverse is of degree 3, so it's 3 to the power of m for m round backwards. So the number of attacked rounds pretty much depends on what the t is and whether we can find sufficiently large linear structure fulfilling this size. Yeah. So here's an example of 2 rounds, linear structure of dimension up to 512. So you only see 1 round here because you can actually extend this state backwards by 1 round, still linear. So I didn't display here, but it's for 2 rounds. So the dimension is 512 because for this column and this column, you can set the variables freely. The only thing you have to deal with is the theta. So we force the variables to be CP kernel. So means for this column, we set the sum to be a constant, and similarly for this column as well. So you actually have 4 free variables in each column. So that adds to 512 bits. And we can do the same for 3 rounds, but with dimension up to 194 only. Again, you can extend this state by inverting its 1 round. It's still linear. And what we do here is something similar. We set the variables freely and force the columns to be in CP kernel. And we do this again for the second round. Means that we force the sum of this one and this one to be 0, sum of this one and this one to be 0 as well. So if we count the number of variables we have, we actually have 10 lanes here. But we have 2 lanes condition here, 5 lanes condition here. So we are left with 3 lanes, each lane of 64 bits. So that up to 192 bits, but there are some internal relations for 2 bits here. So if you work out that detail, it's actually 194 bits for this one. Okay, so we have 2 round linear structure of dimension up to 512, 3 round linear structure of dimension up to 194. So if we use that, we can do some distinguisher for up to 14 rounds using the 3 rounds linear structure, which is of dimension up to 194. So all the sizes, all the algebraic degrees are limited by that 194 if we want to use that one. Yeah. Last one, 15 rounds, we can only use the 2 rounds linear structure because the degree is more than 194 here. So actually, we can attack up to 11 rounds practically, and we actually carried out the experiments on general CPU. Yeah. The last attack I want to mention is the key recovery. So for the key recovery, there are several targets like KMAC, KYAC, and Catcher. For KMAC, is processing the key as an independent block, so preventing it, there might be nonce and sorts. And there will be some padding applied to the message, and this is following sponge again. And the difference between KMAC and KCHAC-MAC is that, so here KMAC is processing the key as an independent block. However, for KCHAC-MAC, key might not be a complete independent block. So this is concatenated with the message. So some message bits might be processed together with the message key. So for KYAC and Catcher, this is it is authenticated encryption submitted to CISA. They are taking the underlying permutation from the KCHAC P family, but with smaller sizes for KYAC. 800 bits and 1600 bits for KYAC, and including some smaller variants for the Catcher. So from the attacker's point of view, after processing the key, the entire internal state becomes, after processing the key and after the application of the permutation, the entire state becomes unknown to the attacker. So this is the difficult part. So the attack methods are called cube attack or cube attack-alike cube analysis. So I guess my colleague Ling already mentioned this on the first day. So I just briefly describe the attack here. So given the Boolean polynomial and the monomial Ti, and I is restricted to a subset, F can be rewritten as Ti times the superpoly of I plus some factor which is not multiple of Ti. And here T, V are the cube variables, and D is the dimension. And the cube sum can be expressed in this way. If we take the sum over all the V's. And for cube attack, the superpoly is linear. And for conditional cube attack, because we want to recover the key, so we want this linear polynomial to be dependent on some keys. So it means that for some key values, this is happening. For some other key values, this is not happening. So depending on whether this is happening, we can recover the key bits. And for cube attack-like cube analysis, we have auxiliary variables, and this this linear polynomial is actually involving lesser key bits. And so of course, in this attack, the algebraic degree of the following rounds is totally depending on the number of rounds, because in each round, the algebraic degree is 2. So once the number of rounds is fixed, the algebraic degree fixed to m, the algebraic degree is 2 to the m. This is not what we can control. So what we can do is to prepend several rounds before this and generate a linear space of dimension at least m, so that this is happening. And usually the first round of the K-P is chosen to be linear, so this can be done easily by carefully choosing the position of the variables, and tools like MILP can be used to find suboptimal or optimal choices of condition, fulfilling this. Yeah. And the result, so I'm not going to the details because this was already discussed on Monday. So the final result is that for Kmac, depending on the key sizes, we can attack either 7 or 9 rounds out of 24. For K-Mac, with key size 128, the maximum is 7 rounds. And for K-Yak and K-Che, so also depending on the key sizes, because this affects the layouts of the variables, we can attack from 6 to 9 rounds in different settings, like non-respecting and non-respecting. And for KJ, depending on the version, we have attacks up to 7 rounds out of 13. And there's a FKD variant of this. So this simply means that you can control the states. Yeah, you can control the full states. So the degree of freedom is generally more than the other designs. So that's why we can attack a bit more rounds than the other variants. So I want to use this last slide to briefly describe the attack on cravat. So cravat was actually proposed in FSC last year. So it's a PIF design, and starting with the master key, it derives the K-in and K-out to mask the inputs and the outputs. And it has 3 layers. The first layer actually accumulates the inputs. So messages are split into blocks and processed by this PC permutation. The output is then added together and then passed to the permutation PD. And this output is rotated by this rolling function at each layer and into another layer of permutation, which is the output is then masked by this K out before outputting the value. So there are generally 2 ways to attack this. Okay, the underlying permutations are K-P. Okay, the number of rounds is actually either 4 or 6, and the rolling function are linear at the very beginning, but after the attack, the rolling function will switch to nonlinear functions. So the general idea is that you have an accumulator here, which is linear. So if you choose 2 different message blocks here, 2 different message blocks, after the PC, it will form an affine subspace of dimension 1, okay? No matter what 2 different message blocks you choose here, you will form an affine subspace of dimension 1. So that's automatic. So if we do this for all the layers, it will form a very big affine subspace here, yeah? So, and then we look at this one. We look at PD plus the PE as one permutation of a few rounds. So if it's 4, then this plus this is a permutation of 8 rounds. If it's 6, then this is a permutation of 12 rounds. We look at this together, and so we actually do meet in the middle, means that we find a big enough affine subspace here, and depending on the algebraic degree, let's say depending on the algebraic degree, if it's for 7 rounds, we can find the algebraic degree is 2 to the power of 7, which is 128. If we can find the affine subspace dimension more than 128, then we can bypass 7 rounds here, and then we just invert 1 round or 2 here, so that we meet in the middle, meaning we do the same. We do the same, but we do the same on the output, but just do the inversion for 1 or 2 rounds here. And then you will encounter a place where the sum is 0 because you apply this cube-like attack on the first few rounds. Yeah, so that's middle, and that's applied to these variants with all the permutations of 4 rounds. And when this is 6 rounds, we can still attack it by taking this rolling function is a linear function into account. So meaning that we actually assume, you notice that y here is the same. We assume this is a variable, and this is unknown. However, since the rolling function is linear, we can actually find the relation between y0 and y1. And this relation, some of the properties will preserve even after a few rounds of PE. And if we can find the same property from backwards, starting from the outputs here, then we can obtain a system of equations to actually solve the y. Yeah? Once the y is out, then the k out is also found. So due to this attack, the designers actually converted this rolling function to a nonlinear rolling function, and all the number of rounds of the permutations are increased from 4 to 6. So in conclusion, 5 and 4 rounds of SHA-3 can be attacked with respect to collision and preimage resistance out of 24. So still there's a very huge security margin. For key recoveries, the 9 rounds only works for the full FDK, so everything can be controlled. However, intensive curve analysis is still necessary when weak permutation is used. By weak, we mean when you have 6 rounds here, already you can see it's not ideal because 6 rounds, the algebraic degree is only up to 64. So already you know it's not ideal. And if you want to use it, you should undergo some intensive analysis. So actually, all the information about the talk are available on this group website. Thank you for your attention.
So we have time for questions. So you have one.
Yep.
Have you looked at the possibility of applying some algebraic attack on a smaller permutation plugged in the cravat construction? For example, the Xudu, I think it's the name, which works on 3 bits. So probably the inverse, then it's simpler to invert because it has degree 2 and not 3, like in the Ketchak-P permutation.
So for cravat, when it is used in cravat, again, I think the rolling function is nonlinear, so all the attacks were stopped by that.
Yes.
But so far, has it been used in any other design? I'm not sure. Yeah. So generally, the attacker is easier when we have more variables under control. So meaning if we have bigger internal states, and so usually that will allocate more degree of freedom for the attacker.
Yes.
And in that scenario, usually you can attack more rounds. So if you reduce the internal state size into smaller variants, if anything else is kept to be the same,
Okay.
Lesser rounds will be attacked, usually.
For sure, yeah. Okay, thank you. Any questions? If not, let's thank Gian again. Yeah. And it's a small break.
Slides on the website? On the FSU website?
Can.
Okay. Just do not delete them.
Okay. Okay.
Do you know how to extend to
Control M.
Okay. Okay, thanks.
Yep.
Thank you. Printer.
This is you can plug it here.
Okay.
On va vérifier heureusement 5 minutes la question. Non, non. J'étais trop occupé à faire mes slides. Ah, j'ai deux trucs. C'est toi qui te gères.
Ouais, ouais, normalement. Enfin, je pense que c'est le moment sur le programme, ouais.
Est-ce que tu pourras juste remettre le programme de la rampe après qu'ils aient mis leur slides
Ah ouais, ok, ouais.
Juste pour que la pause.
Ouais. Ça marche. Je les trouve facilement.
Ouais, ils sont à la racine du dossier des slides.
Ça marche.
C'est sur 2019.
Ok. Okay? Can you just tell me how to pronounce your name? Mustafi Jara. Okay, good. Thanks. Just
Inch'Allah, ça marche.
J'ai la même clé USB quelque part. Je sais plus d'où elle vient.
Fenêtre parce que sinon je sens que... Non, ça va, c'est facile comme chemin en fait. Ah voilà.
Clé bleue.
Ah, je vais l'appeler... Ah bah ouais, je suis... Renommé,
ouais, mais ton nom dedans, ça sera plus facile, ouais.
Gogien. Et on va copier... Ah merde, c'est pas ça. J'arrive plus. Et c'était... Merde. C'était à la racine, non? FSE. Tout le monde voit.
Sur le bureau, peut-être?
Ah, peut-être. Ah oui, FSE slide, super. Moi, je suis à session. Non, mais c'est ça, en fait.
Ouais,
j'ai l'impression que les autres, ils ont mis...
Bah, c'est peut-être session 9, si, à moins que les gens l'aient mis à l'avance.
Ah ouais. Ouais, c'est ça, c'est ça.
Ça colle avec les autres?
Collé, ouais. Je vais vérifier que ça marche bien. Sinon...
Bah ouais, non, vérifie que tout s'affiche bien.
C'est quoi, c'est F?
C'est L, je pense. Ctrl-Shift-L, moi j'aurais dit.
Ctrl-Shift-L?
Ouais, de mémoire.
Ok.
Ouais, ça a l'air. Si t'as des images, vérifie qu'elles s'affichent bien.
Non, j'en ai pas, non. Juste du tics.
S'il n'y a rien de compliqué. Non, mais même si t'as des tics bizarres.
Non, moi il est tout bête mon tics. Regarde,
c'est
un truc gentil ça. Ok, voilà.
Ok, bah très bien. T'es passé où là?
Voilà.
Par contre, il voulait juste qu'on remette la ROM. Ouais, fais gaffe, hein, on a niqué une clé une fois. Ouais.
Ah ouais?
Ouais, enfin, je pense qu'en la reformatant, c'est passé, mais.